So I think it's 7 o'clock. I think we can start. Sir, may I request you to start the proceedings? Oh, I think he got locked out. So we just need to wait for Professor Deshmukh to rejoin. Probably there's some disturbance at his end on the internet connectivity. Let's wait for a couple of minutes. He's back, I think. Professor Deshmukh, are you able to hear us?
Yeah, Arijit, I had got, yes, I had got momentarily, but glad to be back. Yes.
Okay.
So are we ready to start?
Yeah, I think we are good to go.
It is sort of time.
Yeah, it's on time. Yeah, we are just 2 minutes faster. Yeah.
Can you hear me, Arijit?
I think your voice is breaking down.
I think his network connection is very poor.
Yeah, I guess so.
Yeah. Professor Vijayaraghavan, are we ready to go?
Yes, I'm ready.
Professor Vijayaraghavan, can you?
Yes.
Yeah, we are good to go. We are good to go. So I think he got locked out again.
Yeah, his connection sounded very bad. It was showing the network bar was also showing red. So
right. I agree. Sometimes this is a challenge in online meetings and online teachings that, you have students who are possibly, in some area where the network is not that great. And then he or she suffers from the lecture, right? Because, okay, just please wait. I need to take this call. Right. Okay. So that was Professor Deshmukh who just called me and said that she's having network connectivity issues. So I think we'll start, okay, without further delay. So let us welcome Professor Vijayaraghavan from TIFR today, who is our distinguished speaker for the Camost Colloquium series. So he's going to talk about on how to build a quantum computer. And I think, Professor Vijay's lab is one of the pioneers in quantum computing right now in India. He's working on superconducting qubits. So just to give a brief biography about his life so far and his academic journey. So Professor Vijayaraghavan completed his bachelor's degree in physics from St. Stephen's College, Delhi University in 1999. And then he spent a couple of years at the University of Cambridge pursuing a BA in Natural Sciences before starting his PhD at the University of Yale in 2001. At Yale, he developed a new measurement technique for superconducting quantum bits. And then he continued working on improving quantum measurements during his postdoctoral stint at the University of California, Berkeley, which led to the first observation of quantum jumps and the first demonstration of quantum feedback in a solid-state quantum system. Since 2012, Vijay has been the principal investigator at the Quantum Measurement and Control Laboratory at the Tata Institute of Fundamental Research, Mumbai, where the main goal is to develop superior quantum processors and develop techniques to stabilize quantum states against decoherence. Some key highlights of his group's work include development of a broadband, ultra-low noise amplifier for quantum measurements and a novel multi-qubit processor design. He is currently leading several projects to build small-scale quantum processors with funding from DRDO, TCS, and DST. So today, Professor Vijayaraghavan is going to share his wisdom on building quantum computers. And I take this opportunity to welcome everybody who is in this meeting, and especially also our viewers on YouTube as well. Without further delay, I invite Professor Vijayaraghavan to share his presentation and start the discussion.
Thanks a lot, Arijit, for the introduction and also for inviting me to this special occasion. And congratulations on your anniversary of this center, which is a collaboration between these two fantastic institutes in Tirupati.
Thank you.
Hopefully, sometime in the near future, I'll get to visit.
Yes, absolutely. Absolutely. We'd love to have you.
So let me share my screen.
Yeah, I think it's visible. Yeah, full screen also, perfectly fine.
Okay, great. All right, so let me get started. So I hope to give you sort of a very general overview of the different components that go into building a quantum computer. As I also mentioned in the abstract, this will be focused around the superconducting circuit technology, which is my area of expertise. But the general notions do apply to pretty much every technology which is being pursued for building quantum processors, quantum computers or simulators. Just that the specific details of the technology that is used, the kind of electronics you need and the physics you have to exploit to implement the same underlying fundamental operations as well. So I will start by giving a very brief overview of the idea of quantum computing, and then tell you a little bit about the different platforms, and then focus the particular implementation in superconducting circuits. And then towards the end, I will tell you a little bit about the projects we are doing in our group in TIFR, and also in general, some information about how the quantum technology area in general is progressing in India, and what are the opportunities that are available for the young students and researchers alike. Okay, so one very important idea to keep in mind is that information is actually physical. Our conventional today's digital technology works on storing and processing information in the form of bits, which we often represent at 0 and 1. But when you store them, or whether for permanent storage or for processing, you need a physical system which is able to encode this information. And there are many possibilities. Even though the information is the same, the physical system could represent the zeros and ones in different ways. For example, in a DVD, it's different than how it is done in a magnetic disk hard drive or a flash drive, or the states of a transistor inside your central processing unit in a computer. But all of them use the idea of a two-state system, where the two states, the physical states, differ in different implementations, but the information they store is the same, and the logic which is used to process the information is the Boolean logic. And with that, you're able to do all the amazing things, including being able to have this kind of sessions online. And of course, this has been very successful and tremendously powerful, and with great progress made in the last several decades. The idea behind doing something different is now connected to the new possibilities which quantum mechanics offers us, and if you start bringing them into the picture. So what are we talking about? So when we say quantum systems, we usually think about atoms and electrons, because quantum mechanics was sort of developed to explain what was going on in the microscopic world of atoms and electrons and photons. And this immediately allows an additional possibility which is not there in the classical domain. And what do I mean by that? So here's sort of a cartoon picture of, say, a hydrogen atom with a single proton in the center and the electrons orbiting around it. Now, we know that the simplistic picture of the solar system like model with the electrons going around in regular orbits is not correct, but a somewhat cartoonish representation of what might be going on is that you have these probability clouds. That is, there is a region around the nucleus where you have likelihood of finding the probability, and you can have different energies of the electron, and then they will be occupying different orbitals. Now, if we decide that we take, let's say, a hydrogen atom, and we say when the electron is in the lowest energy state, which is the 1s orbital, we could just decide to use that as to represent the state 0, in correspondence with how we store information in the classical domain. So we could call that 0. And here I've represented that as a ket here to represent that this is actually a quantum mechanical state. And then I could choose the next higher energy level, the 2s level, for example, as my 1 state. This is a perfectly valid mapping. Of course, there are issues of practicality that something like this, whether it will, it's easy to control or not, but we will come to that later. Right? So once we make this kind of an assignment, so far it looks exactly like the classical picture, except much more complicated, that you're not talking about controlling electrons and their orbitals in a hydrogen atom. But the difference is that if we use this to store information, then you also have the possibility of creating quantum superpositions. Now, because both these states, the orbital 1s and 2s, they are solutions to the Schrodinger wave equation. And we know that if you have two solutions, then any linear combination of the solution is also a solution for a linear wave equation. And this means that now there is a possibility of creating states like this, which is 0 plus 1. In sort of layman's terms, we sort of like to say that, oh, now the quantum bit is in both 0 and 1 at the same time. But mathematically, of course, in quantum mechanics, we know what that means. This is sort of the best we can do in regular language, unscientific language. But we also know that this superposition doesn't just have to have a plus sign with the same weights. It could also be 0 minus 1. So, then it becomes tricky. Okay, do I call this also 0 and 1 or what? But, I'm just sort of saying some of the peculiarities of invoking the superposition principle in quantum mechanics, which brings it. But we know what this means. And it is perfectly possible to prepare a hydrogen atom's electron in these kind of states. Okay, so this definition or this choice of a physical system to store information is now what is called a quantum bit or a qubit. And it's nothing but a quantum 2-level system. Note that even in the previous example, there are many levels. You have many electron orbitals, but you choose typically the 2 lowest levels and call that your quantum 2-level system. And we only need 2 levels. And that's why it's also referred to as a bit, just like a classical bit has 2 levels. So you have, now it doesn't have to be the atom. It could be any quantum 2-level system. And then the superposition possibilities can be written down like this, where the 0 and 1 state have these coefficients cos theta by 2 and e to the I phi sine theta by 2. This is a convenient parameterization, which basically allows for all the possible superpositions for a 2-level system. It automatically normalizes it because the sum of mod square of these two coefficients is 1, which we need because we know that the total probability of finding the system between 0 and 1 should be 1. Assuming we are confining it to the only 2 states, in a realistic case. Here, there are only 2 levels, so there are no other levels to worry about. Once parameterized like this, it is convenient to represent these states on the surface of a unit sphere. And this is often called the block sphere representation. And then theta and phi basically represent unique points on the surface of the sphere. The original states, which we often call the eigenstates 0 and 1, are represented by the points on the pole. In some representation, you might see the 0 and the 1s interchange positions. That's just a choice, doesn't really matter. All the other points on the surface of the sphere are equally valid superposition states represented by different values of theta and phi. So, in some sense, this is like a GPS coordinate of somebody on the surface of the Earth. There are two numbers, the latitude and longitude. So this is sort of similar to that. And so you can have 0, you can have 1, or you can have something which is along the equator, which would be an equal superposition. So a state like this would have equal magnitudes for both 0 and 1 as well. But the point here is that there are now infinite possibilities of preparing a two-level system, not just the two possibilities which existed in a classical bit, which is just 0 or 1. Because I can choose any point on the surface of the sphere and you can divide it into infinite number of points, and that's perfectly possible. So one common misconception which comes when discussing quantum computing in sort of general terms and the ability of qubits is this question about how much information can one really store in a single qubit. And this is because of this point I just mentioned, that there are these infinite possibilities. So suddenly it seems like, well, if this system has infinite number of states, then essentially I can store infinite amount of information on the surface of the sphere, right? I mean, if you take a trivial example, I could just choose 26 unique points on this sphere to represent the 26 alphabets of the English language. And then in just one qubit, I have encoded all the language, all the alphabets, whereas in a classical system, you would need many more bits to represent all the letters from A to Z. But there is a catch, and that catch is related to the measurement of quantum systems, because a memory is only useful if you can recover the information from it. Okay, so you would like to store your favorite songs on a USB drive or your USB flash drive, and then come back tomorrow and be still able to listen to them. And it should play back exactly the same song and not some garbage or some other song, right? So that is important, that the memory is recoverable. And this is where the problem lies when you start thinking about the superposition states. We know that when we try to probe a quantum system, it usually, depending on the exact details of what the system is, but typically what happens is that you observe this phenomena of quantum collapse, that the system would give you a result which is basically discrete, and it could be, and it has to be one of the eigenvalues of the measurement operator. Now, for a two-level system, we typically measure along using the energy basis, or sometimes it's called the sigma z basis. There are only two possibilities. So when you do measure, we actually get only one of the two possible answers, which we can call 0 and 1, or plus half and minus half, depending on the representation. But that's all you get. And moreover, it's not just that, you get that result randomly, depending on the particular superposition you have created. You cannot predict whether the result would be 0 or 1. You just know that the probability of getting a 0 would be proportional to this alpha square coefficient, and the probability of 1 will be proportional to beta square. So this sounds terrible in the sense that not only it seems like infinite possibilities are not there, but that the result could be completely random. So it's true that if you're just going to put something in a superposition, it's not going to be very useful unless you know exactly how to use it. So even though the encoding possibilities are infinite, the recovery is only one bit. So it sort of emphasizes the correctness of the name quantum bit more as well, is that you can only recover one bit of information from this qubits. Just from the point of view of storage, it doesn't really change anything, right? So that's not where the power of a quantum computer comes from. It really, one has to now think about what happens when you go from a single qubit to many, many qubits. Then the number of different states grow exponentially as 2 to the power n. And then you can create a superposition of all of those 2 to the power n states. And it is there that you're able to access a very large phase space where you can carry out manipulations. But at the end of the day, the measurement is still only going to give you n bits. So whatever process you do has to exploit that particular aspect. Okay? So in general, what you need to build any generic quantum computer is you need some physical system where you can encode these two levels. Again, just showing atomic levels here as an example, but it could be anything. You need the ability to manipulate those states so that you can create any different types of superposition states which you would like. You should be able to measure the quantum states very precisely. This might again seem like a surprising thing to have mentioned here as an important point, but measuring quantum systems was not very easy. It was quite a challenging because they are very, very sensitive, and to measure precisely and get the correct probabilities was non-trivial. In fact, I spent a good part of my PhD and postdoc solving the measurement problem in one of the domains of superconducting qubits, and it's the same situation with many other platforms. In some, it's relatively easier than the others, but it's very important. And it also actually plays a role in the sense that it's not that you do the measurement only at the end, which you do, but when you want to deal with errors in these systems, you have to make measurements as well. So the measurement has to be fast and precise. And then most importantly, you need the ability to create some kind of interaction between the different qubits. So one qubit is not good for anything, anything really useful, and neither is two, and you need many more. But what people have showed is that as long as you can have at least pairs of qubits which can interact, and this is very important to create a special kind of superposition state in multi-qubit systems, which are called entangled states, and they play a crucial role in many of the applications. And for that, you need some kind of an interaction to happen between multiple qubits. So all of this put together would allow you to build a general purpose processor if you can do all of these things well. Okay. So now coming to the choice of physical systems, there are many possibilities, and I'm sure many of you have heard about the different possibilities. Some three popular ones are shown here. On the top left is trapped ions. What you're seeing here is a structure which is able to confine a string of ions, charged atoms, trapped in an electromagnetic field and then being manipulated with laser light. And this inset here sort of showing you that these are in a linear array, and what you're seeing is that they are all glowing and fluorescing the light which is incident about them. And this was one of the first earliest platforms where people were able to manipulate individual quantum systems, and eventually led to the Nobel Prize in 2012. And they are currently one of the most powerful platforms for building quantum processors, because these are microscopic degrees of freedom. They are very well protected from the environment by design, and they obey the laws of quantum mechanics very well. So they are very good qubits, but the flip side is that because of their microscopic size, that it's quite challenging, and decades of work has gone into mastering the ability to control these things very precisely. Another platform, which is quantum dots. Essentially, these are confined electron spins. So you have a 2D electron gas, and by using gate electrodes, sort of shown here in this golden color, you can create an electrostatic potential, but now in a two-dimensional electron gas, and then trap an effective single electron in that. And then you can apply a magnetic field, and the spin of the electron can then be used as a degree of freedom. It can either point along the magnetic field or against the magnetic field that has an energy splitting related to the magnitude of the magnetic field you apply. And then you can manipulate that as a quantum two-level system. This has advantages in the sense that it uses sort of semiconductor processing techniques. This platform has shown some good results, but it has not achieved a lot of multi-qubit results compared to trapped ions or superconducting circuits, which is what we're going to focus on. And here the superconducting circuit differs quite significantly from the other two examples I've given. You can sort of think of the trapped ions as, first of all, natural quantum systems. These atoms are given to you by nature. You cannot really change their properties. If it's a calcium atom, it's a calcium atom, and all calcium atoms are the same. And they also are microscopic degrees of freedom. Similarly, in quantum dots, it's sort of a hybrid thing in between, I would say, because you need special materials to sort of create these 2D electron gas and then effectively trap, but it's still, you're talking about the spin of one electron, which is also a microscopic degree of freedom as compared to a superconducting circuit. I always forget to put a size scale bar here, but this square is about a few microns on side, right? And it's a layer of aluminum, which is a superconductor, on a substrate, which can be silicon or sapphire. And it's a huge structure compared to a single ion or a single electron, if you sort of think about it. Even though, these quantum dots, it's not, the confining region is much bigger than, um, like a very elementary electron size or anything like that. But this is much bigger. This involves many, many, many millions and billions of atoms working together, sort of, in the superconducting state. But under the right conditions, their collective property, this a special collective degree of freedom, can display quantum mechanical effects. So from sort of more a fundamental physics point of view, also these circuits, these superconducting circuits, were very interesting for people because it was a macroscopic system which could eventually show, and it was shown that it displays quantum mechanical behavior, and it behaves almost exactly like the atoms and the electrons, when you just think about them as two-level systems or a few-level systems, even though they are much bigger in size. And all of this is surprising or fascinating because we know that we don't observe quantum phenomena in larger objects, even though a lot of experiments have now shown that it keeps working and we sort of understand it. But it makes it challenging for these superconducting circuits that they are bigger. They also bring in some ease of use because they're much bigger in size. They can couple to other things a lot more easily. It's easier to control, but it also has drawbacks because of that, because it also talks to things which you don't want it to talk to. And we'll come to that in a little bit later in the things. And of course, there are many other platforms. I'm not going to have time to cover them. One can use photons and use their polarization states as a possible implementation for qubits. So horizontal represents 0 and vertical represents 1, for example. And they are sort of making a comeback. They were against some initial experiments. Again, it's a microscopic degree of freedom, very highly protected. And in fact, that's the problem. They're so isolated from everything. They don't like to interact with anything, that it becomes very difficult to control them. But some new experiments have shown that maybe there is a possibility. Some of you might have even heard that there was a photonic processor in China recently, where they have actually demonstrated some very important results in showing that a quantum processor does better than a classical processor. Then you also have versions of the trapped ions, which are cold atoms, which are trapped in optical fields. They are not charged like the ion trap ones. And you also have topological qubits, which are fundamentally protected because of topological arguments. These are these Majorana fermions-based proposals. Of course, there has been recently some retractions of some papers, so we don't know how quickly this field is moving. And then also things like nitrogen vacancy centers in diamond, which have lots of application actually in quantum sensing and also in qubits. So there are many more as well, and new ones could be coming, and maybe tomorrow there'll be a completely new one which might be better than all of these. So in that sense, the field is open, but currently superconducting circuits and trapped ions are considered the two most sort of leading platforms with the quantum dots and the photons and cold atoms sort of nearby for slightly different applications. Okay, so now let's talk about the superconducting circuit itself. What exactly it is? Why we can think of it as a qubit? Sounds strange that an electrical circuit would behave quantum mechanically. And the simplest way to understand is that it really is just an oscillator. And in fact, more specifically, a particular type of superconducting qubit called the transmon qubit is actually like the pendulum. And why the pendulum is because of the nonlinearity in the pendulum's motion. When we all learn about the pendulum as a harmonic oscillator, we always approximate sine theta as theta. But if you don't do that, it's not a linear oscillator. And that has implications, which means that its frequency of oscillation is not independent of the amplitude of the oscillation, which is the case for a harmonic oscillator. So here's a picture now with size scale. So you can see that this whole structure is nearly a millimeter in size. You can actually see it with your naked eye. And then what you have is really these two big pads of aluminum. And then in the middle, there is a device which is called the superconducting quantum interference device, which has these two overlap regions where there is a tunnel junction. So it is a layer of aluminum separated with another layer of aluminum with a very thin layer of aluminum oxide, and then electrons, or more specifically Cooper pairs in the case of a superconducting material, can tunnel through them. And this behaves like a nonlinear inductor. And these two pads can be thought of as a capacitor. So you basically create an inductor and a capacitor, which is an LC circuit. And we know that an LC circuit is like an oscillator. And that's sort of the circuit symbol for that. These two crosses represent the Josephson junctions, and two of them in a loop. It allows you to actually tune the value of the inductance by applying a magnetic flux. Okay, so what is the qubit? It's simply the two lowest energy states of this oscillator. So we go to the ground state of this system. So basically the oscillator with no quanta is called the state 0, and the oscillator with just one quanta of excitation is called state 1. Of course, there's a caveat that we know the ground state of the quantum system has in a harmonic oscillator has half h bar omega energy. So it's not 0 energy, but 0 excess quanta in the system. Okay, so that's it. So you can sort of see the correspondence with the simple electron picture in an atom. It's the lowest energy state here also, and the first excited energy state. And this is quite typical for most qubit systems, that it will be the two lowest states, but it is not always true. You can have some intermediate states which are metastable, and then you can use them as well. Okay, so here's a little bit more detail. Now you have some numbers here. You can look at the inductance value. It's about typically around tens of nanohenry, and the capacitance are again sort of many tens of femtofarad. So these are tiny numbers. And when you sort of put this, and you can just simply use the formula for the LC oscillator for the resonant frequency, and it comes out to be around 5 gigahertz or so. So these are in the microwave regime. And now instead of a parabolic potential for a harmonic oscillator, you have a cosine potential for a Josephson junction. And this is the connection with the pendulum, that in a pendulum, the restoring force is proportional to the sine of the displacement. And here also the restoring force is actually related to the current flowing through the junction. And that is also proportional to the sine of a phase difference across this Josephson junction. And so you have the potential is now the related to the force is sine theta. Your potential, which is force is du dx, is cosine theta, and that means the classical statement I made is that a nonlinear oscillator like a pendulum has an oscillation frequency which is dependent on the amplitude of the oscillation, translates in the quantum picture into the anharmonic oscillator having unequally spaced levels at the bottom of the well, right? So it's exactly the same thing. It's the quantum manifestation, because as you go to higher energy, its oscillation frequency drops. So the difference between these two states is larger than the next two, and then so on and so forth. So which means that now you have different spacings. You can isolate the two lowest levels, just by frequency selectivity, because typically you shine electromagnetic radiation at resonance with these transitions, and that is how you carry out the manipulation. So if omega 0,1 is much different from omega 1,2, then you sort of safely can use this as a two-level system, even though those higher levels do exist, and in many experiments they also play a role. But most of the cases you can ignore them. Okay. The fact that this is a 5 gigahertz oscillator also makes it necessary to go to very low temperatures to operate. There is a side requirement, of course, that we are using superconducting materials. So for that, you have to go to low temperatures. Aluminum has a superconducting transition temperature of around 1 Kelvin, but that is not good enough. We have to go to much lower temperatures of 10 millikelvin so that thermal energy is much smaller than the energy spacing between these two levels, which sort of in temperature units, that is, if I divide both by sides by K Boltzmann, this 5 gigahertz resonator corresponds to about 250 millikelvin, times KB is the energy. And this is very important so that to ensure that thermal noise, thermal energy is basically like a random force on this system, should not cause these levels to get populated, because you want the system to always end up in a known initial state in order to be able to push it to the states you want it to go. Okay, so this is one of the important requirements. And in superconducting qubits, we predominantly do this by just operating at a temperature of around 10 millikelvin, which is what can be achieved in a commercial system. And that ensures that you are deep within this quantum regime, and the probability of exciting the first state or the second state because of thermal noise is extremely small. Okay. There are, of course, caveats that other processes can cause the system to get excited. I will comment about that a little bit later. Okay. And the fact that these are made out of superconducting materials also ensures that there is very little dissipation in these systems. And that is, again, very crucial, because think about what you're trying to do. You're trying to use this as a memory. You want to put something in the excited state and, let's say, store one, or you create a superposition state. If the dissipation is strong, in a pendulum, it stops to oscillate. In the quantum version, it decays back to the ground state. And that is not a good idea, because you're trying to manipulate these quantum states. You don't want the states to be reset periodically in a random fashion because of this process of decay, right? So even if you go to very low temperatures, you still have the process of spontaneous emission, just like atoms spontaneously emit into the 3D vacuum. Here, these circuits can spontaneously emit into the environment, which is basically a one-dimensional transmission line which is connected to these devices. And you want to minimize it, and you do that by minimizing the coupling to this environment and also ensuring that you don't create sources of dissipation in this. So working with superconductors allows you to make basically extremely low loss nonlinear oscillators, and that's essentially a good qubit. Okay. So in order to manipulate and measure these systems, we typically put them inside another cavity. So here's a picture of a cavity, which is basically a piece of copper with a hole drilled into it of a specific size. You can sort of get a sense for the size scale. And right in the middle is the chip. So this sized hole actually creates a microwave frequency resonance in that structure. This is now a regular resonator in the sense that it's linear. And we have put the qubit in the middle. This is where the antinode of the electric field will be for that particular resonant mode. It's TE101 in this case. And this creates an interaction between the two things. Sorry, just 1 second. So this interaction between the qubit and the cavity is important for the measurement physics. And this can be done either in cavities like this, which we often call a 3D cavity with the qubit in the middle, or it can be done in a planar design like this particular image shows here. So this long sort of winding line is a section of transmission line, sort of like a Fabry-Perot resonator on chip. And then there is a qubit here, this square thing here in the middle. This is a design from the IBM group. And they both represent the same physics, just different ways of making the same thing. So there's a linear oscillator, and then there's a nonlinear oscillator coupled to it. And this serves several purposes. The microwave cavity here, in this case, this copper cavity, and in the other case, the transmission line resonator, actually protects the qubit. It controls the interaction of the qubit with the environment. So you can see now that in this structure, the environment is basically coming in from these connectors. Okay. Now there is also the environment of the fact that the copper is a dissipative element, but let's assume that it's a small value compared to this coupling. And this environment is filtered by this cavity before it can reach the or make its impact felt on the qubit. So same way that the qubit actually cannot directly emit into the environment, it has to emit into the cavity, and then the cavity has to emit into the environment. By choosing the frequencies of the qubit and the cavity to be different, you can protect the qubit. Essentially, it's like a filter of the environment. It sort of reduces the density of states available at the qubit transition frequency for it to decay. So also often called, the Purcell effect. The other purpose for this, which is actually the main purpose, is This coupling creates an interaction between the qubit and the cavity modes. They are off resonant, but still they are governed by what's called the Jaynes-Cumming Hamiltonian. And that results in the cavity's frequency to be different for the two different states of the qubit. So the ground state and the excited state have two different resonant frequencies, sort of shown here. And then you can choose a frequency of driving somewhere between the two. And that allows you to detect the state of the qubit by just seeing how microwave light scatters off this cavity. And it basically will give two different phase shifts, which you calibrate a priori, and then you can detect the state of the qubit. And this basically allows you to measure. So now we have the ability to manipulate by sending microwave frequencies at the qubit frequency, and you have the ability to measure as well. Okay. Now, all of this requires many, many different tools and resources. So here's a picture of the inside of a dilution refrigerator. It's basically a bunch of plates connected by tubes and pipes and other things. And the lowest plate here, shown here and marked as 10 millikelvin. This is the part which gets to the lowest temperature. And you just attach your experiments here. So you can sort of see in the background, there is the copper cavity, which is attached with a little L bracket. And anything which is bolted onto this plate will also get to that temperature. There's lots of wires coming down from the top. You can see these are semi-rigid coaxial lines, which allow you to bring the microwave frequency signals in and out. They allow you to manipulate the qubit and measure them. These lines can also bring noise with them from room temperature, which is where all your control electronics is. So you need to make specialized filters for them using special materials which are lossy, so that you can really keep the system cold, because it's not just important to just cool the device. You have to make sure that all the connections which are coming to it are also suppressed in terms of the noise they bring in. So you actually attenuate the signals, you use special filters, you have to use shielding, because these superconducting materials tend to be sensitive to magnetic fields. So you have to protect them from any stray magnetic fields. So often we use superconducting shields and special cryoperm shields. And of course, the device itself goes right in the middle. So I just wanted to give you a sense for what are the different experimental things you have to do in order for it to get to work. Just to go into low temperatures is not enough. You need to do all of these things to get it to work. Okay. So here's again a snapshot of, say, the electrical wiring for the cryogenic case. And this is sort of the wiring and the components shown for a simple 4-qubit experiment. And again, the motivation here is to give you a sense for the complexity. It's not, I mean, once you know it, it's all easy, but just the complexity of how many components go in. So each sort of block here is for one particular qubit, and you can sort of see that these wires are coming to this device in the middle, which is basically a structure for holding 4 qubits. So you have signal attenuators, you have special filters, and then on the output, you have special amplifiers as well, which allow you to amplify the signal by in the lowest noise possible way, and then more amplifiers, and so on and so forth. And you can see a little zoom of that one section to really see the signal path. So signals come in from here. They travel through this device called a circulator, which directs the signal to the device. It interacts with the device, comes back, and goes through a bunch of other components to this first amplifier, and then back up again to the second amplifier. And you need, as I mentioned, all of these different components to do these experiments. Okay. I already mentioned that the manipulation of the state is also done with microwaves, and typically you do that by shining a microwave pulse at the resonant frequency of the ground in the excited state, which is the 2-level system you're using. And by just controlling the amplitude of this pulse, the length of this pulse, and the phase of this oscillation, you can essentially manipulate the state from the initial ground state to anywhere on the Bloch sphere. Okay, these pulses allow you to simply rotate these Bloch vectors on the Bloch sphere and take it to wherever you want. So this is actually how you change the quantum state or implement control on these quantum states. Right? And again, to generate these pulses, you need to have a lot of electronics. And again, the idea is just to give you a snapshot of what's going on. There are these AWGs, or arbitrary waveform generators, which create the pulse envelopes, which will allow you to control the amplitude and the time of the things. They go and then modulate a sinusoidal signal. This is the microwave signal, which is the carrier wave. And then using mixers, you actually create the pulses. You can create pulses for different qubits for different frequencies. So A, B, and C could represent 3 different qubits. And then all of those signals are combined and they go into the device. And then when they come back out, they have to be, again, the information about the phase shift, which tells you the state of the qubit, has to be demodulated. And then they have to go into some kind of a digitizer, which converts the analog into digital, and then you can process it on a computer. There's a lot of locking. You have to make sure the phases are all synchronized. So you have to connect all of these devices together with the backplane for synchronizing signals. And this is essentially what goes on. So the idea here is also to sort of tell you that this is actually not very unique or new at all. This is exactly what happens in radar communication, cell phone communication. Your voice is sort of like the modulating thing. It gets modulated on a microwave signal, which then gets transmitted to some tower, and then comes back to another microwave where the information is decoded. So the electronics and the engineering is very similar. In fact, the frequencies are also very similar. So the superconducting field actually benefited from the telecom industry because of all these microwave sources, etc., were available for relatively low costs and off the shelf and of fairly high quality, which is needed to do these experiments. This is just to contrast with the lasers which are required within the ion trap experiments, which are a lot more expensive, a lot more challenging to use than just a simple micro. These days you can buy a USB powered microwave source. You just plug it into a USB port and it generates a microwave signal of fairly good quality, which is good enough for doing qubit experiments. So that has helped. And of course, now many more companies are making custom devices and instruments for quantum computing applications to speed up the whole process. Okay. So then what you need to do is put all of this together into a sequence of operations, which is implementing the particular quantum algorithm you are trying to operate. This is just a cartoon representation of this. Some of you might be seen this quantum circuit representation. You have n qubits. Each of the qubit has a line on which you can put these gates. You can have single qubit gates which only operate on that. You can have multi-qubit gates which operate on multiple qubit states, and then you can have a measurement at the end. Okay, and every object, this box here, which we call the quantum gate, is nothing but a microwave pulse with a specific set of characteristics, frequency, amplitude, time, phase, and all of that. And you have to calibrate each of these microwave pulses to precisely do the operation you're trying to do. So you have to do this repeatedly and test it and make sure that it's exactly what you need. And we have to constantly correct for it because these parameters can drift over time due to just simple things like the temperature of the room changing, or the properties of your electronics drifting a little bit, and sometimes even the properties of your qubit lifting a little bit. So at the end of the day, a quantum algorithm running on a superconducting processor like this is just a whole bunch of microwave signals going into the device and a whole bunch of microwave signals coming back. And that's basically what goes on in a computer, in a superconducting processor. Same thing would happen in other platforms, just that it could be an optical pulse or some other kind of signal. So the mapping from the gate operation to the particular hardware implementation will change from one hardware to another hardware for the quantum. But otherwise, the overall sort of collection of things is identical for all the different things. Okay, so let me show you some examples of what happens when you make a measurement. And in these for these measurements, I had also mentioned that there are these specialized amplifiers. And one of the early things we did in my lab was develop a slightly superior version of these amplifiers, which again also are made using these Dilution junction based devices. So I won't be discussing the physics of the amplifiers, just to show you what they can actually do. So this graph is showing you 6 different experiments, these 6 different curves here. Each experiment is basically prepare the qubit in the excited state and then just measure the state of the system. So this y-axis is sort of a proxy for the state. It's a voltage, and these dashed lines are telling you that this voltage level corresponds to the qubit being in the state 1, and that one corresponds to the qubit being in state 0. Okay, and what you are observing here is the transition from the excited state to the ground state in real time. These are not averaged measurements. Each one is a single shot measurement. And you can see the very high signal to noise ratio in resolving the difference between state 0 and state 1. And again, it might seem like I'm making a big deal out of this, but 20 years ago when I first started doing this, these signals did not look anything like this. And in fact, in my introduction, the work which Arijit mentioned, that's in this paper, where we were able to see these kind of jumps between the excited and the ground state for the first time in a superconducting qubit. Back in the 80s, this was done in the ion trapped systems, which eventually led to the Nobel Prize. And this was, from the fundamental physics point of view, was a huge surprise at that time. Even though quantum mechanics sort of predicted that this should happen, even people like Schrodinger never believed that, this whole quantum jump is a real thing. They just thought that quantum mechanics can only be applied to a large collection of quantum systems, and you can only talk about the average ensemble behavior. They could never imagine that experiments on individual atoms or individual quantum systems would be possible. And in fact, Schrodinger said that you can't apply those to the cases of a single atom and then you get absurd results. But his apprehensions were not correct, and this is now done routinely. This particular data shown here was taken in our lab in TIFR using one of these kind of amplifiers. And this really allows you to do these very high efficiency real-time measurements of the quantum state. Okay. Now, why does this jump actually happen? This is exactly what I was telling you. This is spontaneous emission of the qubit exciting from its first excited state to the ground state. And even though all of these experiments were done in identical conditions, the time at which it jumps is completely random, right? That's the random process of this spontaneous emission. So typically we have to characterize these time scales over which these jumps happen. And the process of the spontaneous emission is also, or it's called relaxation. And in the NMR language, it is given by this number symbol T1. And it's the average time scale over which a process like this would happen. Okay. And there's another kind of process which one has to worry about, and that is related to the phase. So remember that I showed you, or I mentioned that you can create a superposition state, which could be 0 plus 1, but it could also be 0 minus 1. In general, it could be 0 plus e to the I phi. So that corresponds to this vector pointing, being on the equator, but pointing in any direction. And maintaining that direction precisely is also important because it's a property of the superposition you have created. But there is a process called dephasing, which can randomize that particular direction. So you started out here, but then some random process causes your vector to change randomly anywhere on the equator. And these two combined sort of give you the overall picture of what can happen. And both of these are called decoherence because they change the state of your quantum system in an uncontrolled random way. And sort of that makes it less coherent or makes it lose coherence. So this is called relaxation and this is called dephasing. You can characterize these things in your experiments. And here's an example from our lab again. You prepare the system in the excited state and you measure the probability of finding it in the excited state as a function of a delay time between the excitation pulse and the measurement pulse. So that is the delay time here. And you typically get this exponential decay. So this exponential decay is nothing but sort of the average of these many different jumps. Okay, and you can then fit the exponential decay to a time constant, and in this case it's about 86 microseconds. And there's another experiment to measure the phase error, which I was talking about, the randomization of the phase. So here you get oscillations, which should ideally, if there was no decoherence, should continue forever. But because of this dephasing process, the error causes the amplitude of these oscillations to decay, and you can fit that. And in this particular case, it was about 50 or 83 microseconds. And these are typical numbers for superconducting qubits, though some of the better ones. These are actually some of the best results from our group. which are comparable to the average results in sort of the state-of-the-art system. So IBM has really improved their quality of their qubits, and they routinely now get around 100 microsecond plus. In our lab, the routine numbers are closer to 30 to 40. And this was one good sample. And this is another sort of challenge with superconducting qubits, that there can be variation from device to device, which we don't always fully understand. And depending on the exact process you use to make these devices, and the cleanliness of your clean room, and your tools and other things, and some unknown black magic elements to that as well. Okay, so all of these are of course controlled by the environment. The environment you intend for the qubit to have, and other unintended environments like losses in your materials, or even unpaired electrons in your superconductors, which are called quasi-particles. Okay. So one other really interesting and exciting prospect with superconducting qubits is that you can really build anything you want, in the sense of the Hamiltonian you would like, the kind of energy level structure you would like. Of course, there are some constraints depending on the parameter range you can access in a realistic experiment. But you have essentially three building blocks. You have the Josephson junction, you have a linear inductor, and you have a capacitor. And by combining these three in different circuit forms, you can create different kinds of quantum potentials, which will have different quantized energy levels. So here an example is a double well potential. In the transmon case, it was just a single cosine potential, and that was just the junction and the capacitor. But by adding an inductor of the appropriate size, you can actually create a potential like this when putting the right amount of magnetic flux through this loop. So because of this possibility, over the years, in the last 2 decades approximately of superconducting qubits, you've had many different designs, and they've all been given names. And because I mentioned that they have this anharmonic energy level structure just like real atoms, but these are engineered, they're often called artificial atoms. And this is from a review now almost 8 years old. And there have been some new additions to this, though they're all mostly small deviations from the existing designs, including some from our lab as well. And see, the transmon lies on this axis. The two axes are basically the Josephson energy and the capacitive, the inductive energy and the capacitive energy normalized with respect to the Josephson inductance here. And because the transmon doesn't have any inductor, it lies on this line. And then there are many other possibilities, and more possibilities can be created depending on the exact experiment you want to do, whether it is for quantum computing applications or just general quantum physics kind of applications. Okay, so just one last point about, I did mention that creating interactions between the qubits is very important for creating those entangled states, or what we call 2-qubit gates. And essentially, the physics behind that is that of, one very basic idea is that of coupling oscillators, right? So you have two oscillators, you can couple them together, and in the electrical domain, you can just couple them together with a capacitor, for example. Though there are other structures you could use here. Again, these are all just microwave structures. And this is sort of like the coupled pendulum system. And I'm sure many of you have seen these kind of experiments either in your labs in the undergrad, or on TV or YouTube like this. So this is a video I got from YouTube. And you know what's happening here. These two pendulums have the same resonant frequency. So you set one of them in oscillation. Because they're connected by the same thread, they are able to exchange energy. And you'll see that the first one, which was set off, stops nearly, and then the other one is oscillating with the maximum amplitude, and then they will exchange energy back and forth. We know this phenomena very nicely in the classical domain, but this is exactly the physics which is used to create 2-qubit interactions. So you can cause this exchange of energy from one qubit to the another. And if they are actually initially in superposition states, there is a particular time when you stop the process, you can create entangled states. So, and there are variations of this technique for creating entangled states as well. So the interactions here are again mostly electrical with the help of capacitors, as I showed you in the previous slide. Okay, so once you have these things together, you can start making lots of them on a chip or on a 3D structure, if you like. And here are some examples. So here is a 9-qubit chip from the University of California, Santa Barbara group, which is the same group which is now in Google. So you can see these plus things. So these are the shapes of the capacitor. So these are 9 of them. And these squiggly lines next to them, those are the readout resonators which are connected. You can see control lines coming from here. There is a common control line for the measurement. They're using frequency multiplexing technique. So this is one design. You have a linear array. Here's a 5-qubit design from the IBM group. So there are, sorry, 4-qubit one. There are 1, 2, 3, 4 qubits. And again, there are these squiggly lines for the resonators, readout resonators, but also for connecting the 2 qubits. So here the qubits are right next to each other. So they're sort of connected capacitively. Here the qubits are slightly farther away, and they're actually connected with these squiggly things, which are again Fabry-Perot cavities, which mediate interaction, now allowing you for a slightly longer distance interaction between the qubits. Here's again a 16-qubit version from the IBM group. And of course, once you put all of them in the dilution fridge, you need lots and lots of wires. So here's an image from, again, the IBM group for one of their 50-qubit experiment, I think. So there's lots of microwave wires. You know, you need several wires per qubit. And it's a lot of effort to simplify these things and make them more compact, but it's a fairly complex experiment. As I even showed you, even for 4 qubits, you need lots of electronics. And then, of course, they have all been integrated into even bigger chips. So Google had announced their bristlecone processor a while back. And then a couple of years back, they had the Sycamore processor, which created this big news about solving a problem which a classical, even the most powerful supercomputer on Earth would take about 10,000 years. Of course, there were some controversies about whether it's 10,000 years or a few years or a few minutes, but it was a first important step to show that when sufficiently large quantum systems, controlled engineered quantum systems are built, you will be able to really benefit the advantages of exploiting the superposition and entanglement, things like that. Okay. Now, what do we actually do with this? So in the last part of the talk, I will tell you some examples. I'm sure many of you are already familiar with it, but one of the more exciting and sort of the origin of thinking about building these machines was really this fact that doing quantum mechanical calculations on a conventional computer is very, very hard. And it's for the same reason why a quantum computer is powerful, sort of the inverse reason. It's because when you try to represent quantum systems, and solve Schrodinger equations, the degrees of freedom you have to keep track grows exponentially with the size of the problem, or in qubit language, the number of qubits. So, it's like if you need an n qubit system, you need 2 to the n sort of order numbers to be stored, and that 2 to the n can become very big. But if we had n qubits, physical qubits, then that's all you need, and you have to create the right interactions. Now that is harder, and you have to control them, but that's essentially the idea, that the classical resources required to simulate a quantum computer blow up exponentially, but the quantum resources required to represent a quantum problem will only grow, in the same order as the problem is growing, maybe with a little bit of overhead. And the idea is that maybe there's a problem you're interested in, which is directly intractable, but now you have a set of controlled quantum system and you make it mimic the behavior of the physical system you're interested in. And this can be done in analog or digital fashion. Digital means you have a universal quantum computer and you write programs, or different programs means different simulations. Or you can build a custom system, which is sort of like an analog computer, which directly mimics the physical system you're trying to understand. And then you can sort of understand. And Feynman was very excited about this, and he understood that it's not going to be easy. And essentially, this is possible because of the equivalence of, quantum information. 1 bit stored in an atom is the same as 1 bit stored in an electron spin. Okay, so this, I think, from the perspective of scientists and physicists and others, this is one of the most exciting applications, because it will allow you to do all kinds of complicated computations on a computer, and you might actually never have to do it. So some examples, people have done some very basic, these might even look very funny and simplistic, but these are all proof of principle experiments. So these experiments done by the IBM group in 2017, they calculated sort of the bond length, essentially solving the problem of energy versus atomic distance. For a hydrogen atom, a lithium hydride and a beryllium dihydride, they used a 7-qubit processor. So here they needed 2 qubits. For this one, they needed 4 qubits. And for this one, they needed 6 qubits. And these are so simple that you can actually compute these solutions by hand, analytically. Sorry, not by hand, but analytically. And those are the dashed curves. And the dots are the experimental results. So you can see that the matching is pretty good for the hydrogen, but not so great for the lithium. But it sort of seems to follow the trend somehow. And this is all, the reason it's not so good is because of the decoherence effect, which randomize your algorithm as it's proceeding. And later on, 2 years after that, and this is actually uses something called the variational quantum eigensolver, which uses a combination of doing things on the quantum processor and a regular classical processor as well. And 2 years after that, they used some error mitigation techniques. Essentially, they realized how the errors are affecting the result. And by studying them and tuning the error rate, actually, they actually made the errors worse. But then they could sort of extrapolate back and say that, okay, if the errors were not present, and this is because they model their errors and they assume that they understand it. And if the understanding and modeling is correct, you're able to sort of extrapolate back. And these are results from 2019 for the hydrogen and the lithium hydride. Look at the points which are actually lying on the curve. The other points are the one which they actually do the experiment to study as a function of tuning of the error rates, and then they extrapolate back and calculate these things. So this they call error mitigation. You're not getting rid of the errors, but you're sort of working around them. And many such techniques will be needed till we find a way to fix the errors using what is called quantum error correction. I won't have time to talk about error correction at all today. Okay, and similar other experiments have been done again in superconducting qubits, sort of modeling how photosynthesis works. And here's apparently there's an important question of how the photo excitation, when it falls on chlorophyll, is converted into a bunch of excitations which go on further the chain. And especially because this system is very strongly interacting with the environment. And typically we don't consider quantum effects in systems which are very strongly interacting with the environment, because you'll say that decoherence will kill everything. But what they were able to show in a sort of a scale down model by factor of 10 to the 5, these are the energy scales and things like that, in a superconducting circuit, that actually the environmental noise plays a role in enhancing the efficiency of this process. So this was again from a few years back from the group of Andreas Walroff in Zurich. Of course, there are many algorithms as well. So those are sort of more sciencey applications. And in algorithms, again, many of you I'm sure have heard about the Shor's factoring algorithm, which is about finding prime factors of large numbers. And that's a well-known problem which grows exponentially. The complexity grows exponentially with the size of the problem. And so the reverse of actually finding the prime factors. So multiplying 2 prime numbers is easy, but if I give you the product, finding the 2 factors is exponentially hard. And for a large enough number, this problem can be impossible. It could take some enormous number. But Shor developed a quantum algorithm in '94, which showed that it can actually be done. And the complexity no longer scales exponentially, but sort of polynomially. So you can do that. And this has security implications, because this hardness of finding prime factors is a key technique used for encrypting data. It's called the RSA encryption scheme. And if a quantum computer is built which is big and powerful enough, those encryption techniques will fail. There's also the search algorithm in 1996, actually developed by Indian scientist Love Grover, who was working at Bell Labs at that time. And this was related to searching an unsorted database. This is sort of like finding a telephone number in a phone book. Again, I think the younger audience here probably has never seen a telephone directory, but all of us used to have growing up this big fat book which had all the names of people arranged alphabetically, but the numbers, if somebody give you a number and asks you to find out whose number that is, you have no option but just to search randomly or serially. And the larger the database, the time will grow linearly with that. But using a quantum version of the algorithm, it sort of looks at all the options in a superposition. He was able to show that instead of n, it will grow somewhat slower, so it's faster to do it in the quantum version. And in fact, it's these two algorithm developments in 94 and 96 which sort of really kickstarted the hardware development into the next year, because people realized that there are some really powerful applications. And there are many, many possibilities, right? So we talked about doing it for chemistry. So, you can simulate chemical reactions. I sort of imagine a future where you just do chemical reactions on a computer and not actually in the lab until everything is perfected. You don't have to go to the factory floor to say manufacture something. The same applies for developing medicines. You can study these molecules, make them more stable, reduce their interactions. I mean, these are fairly futuristic and things which people imagine, but potentially all of these things should be possible once sufficiently large materials computer is available. And there are even other applications for, like, you can do high energy physics simulations. More on the industry side, of course, materials and drugs are also industry, but things like, image detection, logistics routing, the traveling salesman problem is again a well-known and important problem for, shipping companies, to find the optimal route, and quantum computers are supposed to do better in those areas as well. And things like weather prediction and many, many more, we still don't know. We haven't really tapped into all the possibilities. And part of the challenge is that writing quantum algorithms for a specific problem is non-trivial. It's not the same as writing just a regular program. You really need a different kind of an intuition to understand how the superposition and causing the interference of the different quantum states and using entanglement to really speed up a problem. It requires a separate type of intuition. So it's a hard and challenging field in terms of developing new good algorithms, but people are making progress. So I'll now sort of wrap up by telling you a little bit about some of the talks. So Arijit, another 5 minutes is okay?
Yeah, I think it's fine.
Yeah, and before we pause for the questions?
Yes. Please go ahead.
Okay, so one thing I had mentioned earlier is that, you have this flexibility to design different kinds of circuits just by using these inductors and capacitors and Josephson junctions. So here's an example where we put together 4 Josephson junctions and sort of 6 capacitors effectively in a structure like this. In terms of making the device, it was trivial extension of the standard device I showed you earlier. But what this does is that because of the 4 junctions and the capacitors, it actually creates a circuit which has 3 modes of oscillation. And earlier you had only 1 mode of oscillation, so it was like 1 qubit. So now you have 3 modes of oscillation, and these modes of oscillations have different frequencies, and we have engineered that by choosing the capacitances and basically this structure here appropriately. And it creates a system of 3 coupled unharmonic oscillators. And this translates into a system of 8-level Hilbert space, which is basically the Hilbert space of 3 qubits. 2 to the 3 is 8. And here are all the possible states labeled, and each of these states are connected by these, these arrows, which represent the transition frequencies, and they're grouped into 3 colors as well. And essentially what we were able to show is that we can manipulate this 8-level Hilbert space very, very precisely by just shining, pulses at these 12 different frequencies. And they're grouped into 3 because they sort of belong to one of the 3 qubits. But you really cannot isolate the qubits here, because the qubits are not 3 different physical objects. They are 3 ways of oscillating of the same circuit. It's kind of like thinking of a guitar string and saying that, okay, it has a fundamental mode and then it has a second harmonic. Here, they are not harmonics, but it's a more extended object. So it has several normal modes which are close to each other. And those normal modes now represent qubits, and they are nonlinear because they are, again, containing Josephson junctions. And this Hilbert space is drawn with only 2 levels of each of the normal modes. Otherwise, there will be higher levels hereby. In fact, they are one of the things which make this thing a little complicated. And the transition now, for example, this red one represents the transition of the red qubit, which is the first qubit, but only when the other 2 qubits are in 0, 0. The next red transition is also a transition on the first qubit because it takes 0 to 1, but only when the other 2 qubits are in the state 1 and 0, and so on and so forth. So this one is for 0, 1, and then 1, 1. So each qubit has sort of 4 conditional transitions depending on the 4 possibilities of the other 2 qubits. So this actually gives rise to a very powerful way of doing computation here, because these are conditional transitions, which in this language actually is a 3 qubit gate. So in a conventional single qubit oscillator system, the simplest operations are single qubit gates. Here it's sort of reverse. The simplest operations are 3 qubit gates, because the qubits are always coupled, and you can really think of this as 3-level system. And we were able to show that doing something like this actually has some advantages. In certain algorithms, you can implement things in a much faster with less number of steps, because you have access to these different kinds of gates. And one particular algorithm we did was the Grover search algorithm on a 3 qubit system. And basically, we were able to do the Grover's algorithm only one step. You need several steps, which depends on the number of qubits you're using. In this case, the probability of getting the correct answer can be at maximum 78.125%. That's the calculated number, because you're not completing the algorithm. And the reason for that is that if you had completed the algorithm, the decoherence would have introduced way more errors than the improvement in the accuracy of the answer done by the second step. So this was sort of something, but we realized that till that time, most people had only done single step systems for the same reason. And what we got for the experiment was somewhere between 40 to 55%. These represent the searching these 8 possible numbers, which you can encode in 3 qubits. So we sort of basically said, did the experiment for all the possibilities. And this ranged from 41 to 55. And essentially, it's because of this variation is also because of decoherence, because the 111 state is the highest state and has many ways of decaying. So it decays a lot faster. So hence the error is larger. So the success probability falls down. What was interesting was that when we sort of looked at all of this result and looked at the average probability, the best results at that time was actually in a 5 qubit trapped ion system. And their mean success rate was only about 39%. And this was another system where actually every qubit is connected to every other qubit in terms of which gates they can do. And I'll say something about this in the next few slides as well. And then we actually were able to run this on the free IBM cloud processors very recently, maybe about a year back, and we got about 45%. So we were sort of doing better than some of these state-of-the-art machines as well. And this is really because of these special abilities in this structure, especially the native gates, which are 3 qubits. Okay. So this connectivity is really another important fact. Remember that typically these qubits have to be laid down in a 2D structure, which means, and you have to create some physical interactions between them. So in a 2D thing, you can sort of at the best do only something like this. Maybe you can put the diagonals as well, but then putting the other diagonal will require some kind of crossover. And that's been challenging. And there are other complications with that. So we very recently did this work where we had this idea of using a circular coupling element, which is basically the same squiggly line, but just wrapped around itself with a proper choice of the length, and distributing the qubits all along the circumference. And by choosing the positions of the qubits and the frequency of the qubits and this transmission line's frequency, what we were able to show that we can get a connectivity of something like this. So even though this qubit is far away from this qubit, it actually is very strongly connected to it through the mediating lines. So we are able to show that in this 12 qubit system where there are 30-degree spacings, each qubit is connected to 9 other qubits. So this is a very new result, and we're quite excited about doing this. And here's what it looks like in the actual experiment. Again, we did it in 3D geometry. So these are machined pieces of aluminum, a few inches across of square. And the microwave resonators are shown here. And you can see the circular transmission line in the middle. And the chips are placed sort of between this spoke here and the center line. So these things which are sticking out are the measurement resonators. The signal actually comes from the top through these holes with the help of those connectors, and the chip is placed in between. And we were able to verify this idea that the coupling is reasonably uniform. This is one point at 120 degrees where there is no coupling. And this is basically because you have destructive interference of the signal going in one direction and the other direction. And we were able to compare it with our simulations and show that it works. There are some mismatches, which is mostly due to the placement errors because these chips are placed manually. So if that can be improved, you can even make the adjustment, the accuracy of these things quite well. Okay, so that was about our work. I just have a couple more slides to really talk about what people who are interested in getting into this field, what are the different options? This is a highly interdisciplinary field. Okay, we need, say, theoretical physicists and theoretical engineers to work on new device designs and analyze the noise sources. So there's a lot of modeling the Hamiltonian, modeling the device kind of work. We need engineers and experimental physicists to actually solve architecture problems. So you saw some examples, find scalable solutions which can be made in larger sizes easily without lots of challenging steps in between. We still need to invent new algorithms. We have only barely scratched the surface, and maybe especially things which can run on hardware which is sort of available today. As I mentioned, all of these hardware don't have error correction, so they do make errors. So that's why they're not very good. But maybe by designing the algorithm, you can minimize the effect of the errors. And I gave you this example of error mitigation by the IBM group. We also need chemists and biologists to sort of interact with physicists and computer scientists to really think about the kind of problems that could be mapped onto a quantum computer and really exploit the unique features which is available to all of it. And of course, everything has to work. So it really takes a gigantic team to get all of these things work. So there is opportunities for people from lots of different fields. And this is really an exciting time in India because in the last few years, a lot of stuff has happened in terms of access to funding and new labs coming up. A particular one is the Quantum Enabled Science and Technology, which is by DST. It was just sanctioned last year. About 50 projects have been funded with an expense of about 200 crores. It's supposed to be a 3-year project. New centers of excellence have come up at IISc and RRI. There is a new quantum technology hub, technology innovation hub at IISER Pune, which is again a 5-year project with about 180 crores. There is Center for Quantum Innovation, IIT Madras. The DRDO started a young scientist lab in quantum technologies. And in fact, I have collaborations with them, and we're working on a project to build India's first superconducting processor, which will be available on the cloud. There are also other affiliated experiments in communication, for example, using satellites. And you must have heard about the big Chinese result from 3 years ago about sending entangled photons using satellites. And there's a collaboration between RRI and ISRO, and more people have joined this. IISc recently started the Quantum Technology Initiative, and there's lots of seminar series, new MTech courses, startups, and even your own center for this Camost Center is an effort to push quantum technology. So there's a lot happening, and the big daddy of all of this, as many of you might have heard, is the National Mission of Quantum Technology and Applications, which was announced last year in the budget. With a potential investment of about $1 billion or 8,000 crores. So I was involved in some of the preparation for this mission, and it's supposed to be announced soon. And that will really give a big push as well. So there's lots and lots of opportunities for many people. Okay, so that's basically it. So I think coming back to the topic, computing with quantum bits can really provide tremendous power, exploiting superposition and entanglement. And currently, superconducting circuits, appear to be a strong candidate for building a practical processes, but the ion traps are constantly nudging ahead. And even though it looks like a lot has happened, I still feel it's just the beginning of, it's of a different phase, but it's still the beginning. We need lots of new ideas. And it is in this context, I often have told, even the government officials and other people in the discussion for the mission is that, are we already behind? Yes, we are behind, but I think breakthroughs are still needed. And if we start quickly and promptly and efficiently now, those breakthroughs could come from research in India as well. So there's a lot of excitement and exciting possibilities ahead. And already small-scale quantum processors have demonstrated quantum advantage, basically to say that they will do better than any other classical processor which is available at that time. Okay, so I'll stop there and take any questions. Thank you.
Right. So thank you, Professor Vijay, for a wonderful exposition on superconducting qubits and also summarizing all the developments that have happened in the field. and also giving us the perspective on the Indian science domain, what we have been able to achieve so far, and what the future holds for us. So there are already some questions in the chat box I can see, but probably due to shortage of time, we will stick to a few ones. So there's one question which I can see is, what about when we make a usable qubit based on a quantum computer, how difficult is it to scale to an n-dimensional qubit-based computer? So that's the first question. And the follow-up question to that is, are there any difficulties, fundamentally different difficulties in going from, let's say, the qubit regime to the qubit regime?
Okay. So I guess the question is related to why a two-level system, not something larger, right?
Right.
It's sort of similar. The answer is somewhat similar to why in classical computing also we use just bits. It's technically perfectly possible to create a logic system which uses more than just two levels. It just turns out that it's a lot more efficient and simple in terms of hardware implementation. Similarly, in quantum computing, it was shown that with bits, essentially you can do any universal operation. However, in the near term, when we are trying to solve various challenges, we don't have a blueprint for a perfect quantum computer as of now, right? We are trying to solve these challenges. So in fact, the Trimon example from our own group can be thought of as an alternate model which uses an 8-level system. And it's not just that it's any 8 levels, right? It has to be 8 levels which can be manipulated in a universal way, which means I should be able to do unitary operations, which is basically what the gates do, to take any 3-qubit state to any other 3-qubit state. And that should be possible in a simple way. And that can be done if you are able to design your system correctly. So in our case, that was indeed the case. But there are pros and cons for that. But when you talk about creating technology where you want to have thousands or millions of qubits, then it is better to keep it as simple as possible. So unless somebody shows that there is a technological advantage where going to a qubit, a 3 or 4 or 8 level system gives you a technological advantage compared to a qubit, then this is not going to be needed. But for specialized cases, absolutely true. And our experiment is an example in that. And we are trying to push it further and to say that, okay, instead of using many qubits, why don't we use this 8-level system and use them as building blocks? And in fact, one of my PhD students is going to give his pre-thesis seminar tomorrow, where he has worked on one such idea of how to scale these what we call multimodal qubits. So there is no fundamental reason. It's more of a practical reason for doing that. And as of today, I think all options are on the table. But just from the extrapolating from the classical system, we would assume that a qubit-based system might be easier to work with than a qubit-based system when you talk about scaling to very large number of qubits.
Yeah, Vijayaraghavan, I suspect the angle of that question was more about getting to the fundamentals. So is qubit the basic building block, or is there anything to gain by considering a qubit as a building block? Is that might be the angle at which?
Yes, and as I said, fundamentally, no, is my understanding.
Yeah.
Practically speaking, yes.
Yeah, sure.
Yeah.
Sure. Yeah. Okay. So I will take another question, which is related to the different platforms that are available for quantum computing right now. You highlighted some of them at the early stage of the talk. And a question related to that is it possible to make customized quantum computers that is using different platforms depending on the specific task? And then you can benefit from the pros and cons of each specific platform, right? So basically talking about a hybrid architecture, so to say, right? So, what are the possibilities in this league?
People have been working on it, and today, as you said, there are there are pros and cons of certain systems. For example, atomic memories or ion trap based qubits have higher coherence time, so they are better in terms of memory, you can say. But because they are more difficult to manipulate, you can say that they're less better at processing, because processing means changing states, right? So one could imagine a hybrid system where, trapped ions are used, or cold atoms are used as memory, and superconducting qubits are used for processing. But then you need a mechanism to exchange the quantum information from one platform to the other in an efficient fashion. You shouldn't have any losses happening there, that you're losing quantum information. And that is not always straightforward. The compatibility of the different technologies might not exist. People have actually tried experiments where they have a superconducting resonator, and then on top of that, there's a cloud of atoms which are trapped. And then they try to create interaction between them. Most of these experiments are at the level of proof of principle. Often, trapped ion and other technologies use optical light. Getting optical light very close to a superconductor can be damaging because it's very high energy. It will break the Cooper pairs. So there are these kind of interesting technological challenges, but people are working on it. In fact, a holy grail in the superconducting circuit sort of community is the ability to convert information from a microwave oscillator to an optical mode, and vice versa. And if this can be done in an efficient fashion, the moments you turn the information into light, then long distance networks also become a lot more easier. And it also becomes easier to interface with other kinds of quantum systems where you can trap them. So it is entirely possible that a hybrid system might be needed to build a full-fledged quantum computer. Maybe there might be a special purpose. But as of now, none of the fields has, it's not that we have decided that superconducting qubits cannot become more coherent. Right. That limit has not been reached. Similarly, we have not come to any fundamental conclusion that trapped ions cannot be made faster.
Right.
So until something like that happens, or a compromise is needed to solve the overall problem of getting a working processor, these hybrid things will be, will only be sort of things of interest, but maybe not necessarily a technological push to combine that. Right now, each of them has sufficient problems to work out before we start combining them. But work
right. I agree. So in fact, just to add to your point, recently there's been a lot of work done by the Harvard and MIT groups and the group at Paris, where they're using the Rydberg atom for quantum computing, right?
Yes.
And they have been able to scale it up to 256 qubits, right? So I think the possibilities are enormous, and I think the community is still not hinged up on a particular platform.
Absolutely not. Yeah. I mean, each group, of course, has to sell their own platforms.
Right.
Well, and also because your experience is in that platform, you see easy paths ahead for you, but other things might look a lot more complicated. But it's
sure.
Superconducting qubits and ion traps have been going back and forth, pretty much for the past 20 years since I started my PhD.
I completely agree, yeah.
Right now, it looks like ion traps are ahead, actually, in some overall metric. So we'll have to see.
Sure. And I will take one last question because of the...
Yeah, Arijit, I'm okay with time. Like, I'm happy to hang around for more if there are questions, but you
on
your overall session.
Okay, fair enough. So maybe I'll take a couple of questions then. So there's one question on the applications of quantum computing in artificial intelligence or machine learning.
Okay, so here there are a few different kinds of things that are being considered. Of course, artificial intelligence is not my own area of domain, though I have started looking at some machine learning things. So one area is actually using machine learning techniques to develop quantum algorithms, to develop better quantum processes. So this is actually a conventional use of machine learning, but you are trying to use it to improve the technology that is possible or the algorithms that's possible. Just very recently, I think a couple of days back, someone sent me a link about a quantum machine learning algorithm, machine learning algorithm, which is a classical algorithm, inventing new kinds of quantum algorithms, right? That is one possibility. The other one, which is sort of, I guess, would be considered maybe more conventional, if when you try to combine quantum computing and machine learning is that conventional machine learning follows the rules of classical computing. Now you open up the space and you say, okay, now in the quantum computing domain, there are new rules. So the machine learning algorithm has to incorporate those rules and work around. So that is a completely new domain. So that would be maybe true quantum machine learning, that it's a quantum system which is doing the machine learning, as opposed to a classical machine learning algorithm controlling the quantum system. There the possibilities are, I mean, really endless. But I have not heard of any very specific concrete examples, but there is work happening. But again, just like writing a quantum algorithm is hard, to do quantum machine learning on the using the laws of quantum and exploiting that seems even harder to me. At least this is, I cannot really make any predictions there. But these are the two sort of areas where machine learning and quantum computing are coming together.
Okay. I'll take the final question for the session. So does tunneling out of the Josephson junctions have any effect on superconducting qubit and performance of the qubit?
The tunneling out of the Josephson junction, is that the phrase?
Yeah, that's what the phrase is, yes.
Well, so when I mentioned tunneling in the Josephson junctions, I was actually talking about tunneling from one superconductor to the other superconductor. In the superconducting regime, this tunneling is actually a coherent process. And in fact, it's integral to modeling the Josephson junction as a nonlinear inductor. Now, maybe what you're alluding to is what is often called the current bias Josephson junction, where you send a large DC current and then you get a sort of a washboard potential, which has a metastable state. Now, those kind of systems were used in one of the qubit designs called the phase qubit for actually doing the measurement. So what happened was that instead of a flat, cosine potential, it was a tilted one. So if you escaped out of one well, then you just run down the well, and that creates a big voltage signal, and that was used. But it turned out that in that process, it created lots of unpaired electrons, which took a long time to recombine. And unpaired electron means normal transport, which means dissipation, like finite dissipation in the system. So that circuit was more or less abandoned. All superconducting circuits these days, like qubits these days, they work very much below the critical current, which is basically when the superconductivity breaks down in a Josephson junction. So you're far away from that limit, and you are always deep in the superconducting regime. So the coherent tunneling has no effect on that stuff.
Okay. I think that answers the question that was posed. So with that, we will wrap up the Q&A session for today's colloquium. And I take this opportunity to thank Professor Vijayaraghavan once again for accepting our invitation and giving us this wonderful exposition on quantum computing, and especially talking about his own work on superconducting qubits as well. So thank you very much once again. And I would also like to thank our two directors, Director of IIT Tirupati and IIT Tirupati, in encouraging us and in providing the direction to go ahead with the different programs that we have envisaged for the center. So thanks to all the members of the audience who have tuned in, and hopefully we will have a very good session tomorrow also, where we have Professor Urvashi Sinha from the Raman Institute in Bangalore talking about photonic circuits in quantum communication. So with that, I think we will bring an end to this session, and thank you all. Wish you all a very good time.
Thank you.
Arijit, this is a great evening for Camost because both IIT Tirupati and IISER Tirupati, who are hosting Camost, have undertaken some sort of a major commitment to work in this area of quantum information science and quantum technologies. And as I'm sure Vijayaraghavan is aware, the IIT has also signed an MOU with the Center for Quantum Engineering Research and Education of the Chatterjee Group. And Vijayaraghavan, I'm aware, is also associated with that. I believe in the audience, there are some people from the Chatterjee Group. I think I saw Bhupin. They've been the in the audience.
Yeah,
So,
I saw it.
So I think it's very nice that people are coming together in this very important area so it augurs well for the future.
Yeah, surely, indeed.
Thank you very much, Vijayaraghavan.
Thanks.
It's
And thanks for the
wonderful
invitation.
talk.
Pleasure. Bye-bye.
Bye. Good night. Thank you very much.
Okay, goodbye, everybody.
Goodbye.
Take care. All the best. Bye-bye.
Bye.
Thank you, John. Goodbye.